Okay, so history. So if you have a fish function or fish variable and you want to track its value over your model as it's cycling or between different stages, then you can basically assign it as define it as a history. And what that will let you do is track it. And I believe it's per step, but you might also be able to specify it. I have to double check on that. Yeah, sorry, there's a history interval. So I think by default it's 1, but if you wanted to update that every 100 steps or something, so you don't have overwhelmed with data. But it's kind of nice because once you have that, you can plot it as a history chart. You can plot it against other data right in FLAC2D. You can list the data, or you can export it to a file, a CSV file, and then you could bring that into Excel. If you plot it as a chart, you can just automatically right-click, export to a CVS file. CSV. Every time I hear the drugstore, I flip the 2 letters. Okay, so all we're doing in this example is generating a 1x2 zone model. It's Marcoulomb in this case with some Marcoulomb properties. We're fixing the base to have it has no velocity. So since it doesn't have a velocity, when we fix it, it's at 0. So essentially we are putting a boundary condition on the base so that when we start cycling, it stays in place. Because we're going to apply a velocity in the y direction, so in the downward direction because it's a negative value, y is up positive, at a range of position y equals 2. So at the top of the model, because it's 2 zones, so at the top it'll be a value of 2, coordinate 2. The bottom it's 0, so 0, 1, 2 in the y direction. So along that range, we're going to apply a very small velocity of 1 times 10 to the negative 5. And I'm sure they pointed out to you that we don't actually specify units, but we use a consistent coordinate system. So if you want to work with meters or with kilograms per cubic meters, that kind of controls what everything else has to be. Or you prefer to work in megapascals or in PSI or something like that. Although it gets a little crazy with PSI, we've got slugs and snails because they're like mass units. So it's well documented in the manual though, and there's conversion factors. So it's just like converting to like a mass and metric. Okay, so a couple of things. What we're going to do first is identify the position of the history we want to do. So let me move to this here. So this is the origin. That's 0. That's 2. And in this corner here, it's a little hard to see in this plot, but there's a black dot here. And that's the history when we want to track for whatever reason. There's 2 histories that we're tracking. So remember this, but what we have here is a point here and a point here. So we can use this built-in function called gp.near. So I want to find the grid point that's near that Cartesian coordinate. They happen to exactly align because that's the way the model was built. But you could imagine you've got some actual topography and you want to find a grid point near that. So it will grab the nearest one, and we can track maybe displacement. So maybe you're mining underneath this surface and it's going to start to cave in. We want to measure that displacement, compare that to satellite information. In this case, we're just going to we're just looking for a couple of grid points, and they happen to be at 0, 2, and 2, 2, which is here and here. And that's all we're doing here, and we're assigning these to variables, address 1, address 2. Then we're going to create a function, a fish function called load, which is just going to be the sum of the unbalanced forces in the y direction for those two grid points. So these addresses, I mean, we could have just put this bit of code in here, but this kind of helps make it a little more readable. So this is just a built-in function. It's an unbalanced force function at a grid point in the y direction. It could be x if we were interested in something happening in the x direction. And we're just summing them. Doesn't matter why, it's just what we're doing. And then by invoking fish history load, load is this thing that we've defined. It has no other meaning in the model. It doesn't refer to something that's intrinsic or that you could plot. I mean, you could plot these individually and you'd see the vectors at those grid points, but you wouldn't see the sum of them. So you could imagine we've got forces, you know, the area or the length, so we could get like a stress if we were going that way. We haven't assigned it any ID, but by default, the first history you make is history 1. So fish history load, that means that every step it's going to basically go and say, what's the unbalanced forces at those grid points in the y direction and sum them up. And it's just going to keep doing that every step. If we change the interval to 100, it would do it every 100 steps. And then this last thing is just another history that we're tracking. In this case, we're basically looking at the y displacement at position 02, which is what this black dot is, for a zone. So as a command, we can assign histories because displacement y is a built-in thing that it's always recording, right? Whereas this fish function is something that we've calculated for whatever reason. That isn't sort of something we can just see or plot or measure in the software. So this is a custom history, and this is sort of a built-in history. And because it's a second history, it's history 2. We're just turning off large strain because, again, it's basically going to just try to squeeze the model. It's fixed at the base and a very slow velocity at the top. And we're just going to step 1,000 steps. So if we run that exercise, and note, there's a bunch of stuff here with plot information. We'll talk about that in a second, but just everything up to line 28 we're going to run, where it says program return. And that command program return is used if you're calling a data file from another data file. So sometimes people will set up a whole bunch of data files to do different parts of their model so they can kind of organize it. Some people prefer just to have one giant model and then document this does that. But you could imagine if you've got some function that you're always using all the time for a lot of your work, you might want to have that as like a library file or something. And you just have that, you can bring it into your new project. And then we have quite often like driver files or master files, which just run the other data files in a particular order. And so what the return does, program return says, go back to the program that called you or the data file that called you. So when it gets to the end of this second, say you've got a data file that calls this data file, and this data file finishes running, it'll go back to the last position in the previous one. So there might be additional code under that to do more stuff. That's kind of a handy way to just bounce back. So let's run that. Okay, it cycled pretty fast. And now what I'm going to say, have you do is let's highlight all this plot stuff down to the bottom and run that. So what it's going to do is generate the plot that I had in the slide. So with that, two things. One, how did we get all those commands? So if we've got a plot and I right click on it, under export, there's this option called data file. Click that, call it plotter or whatever you like. So now what it's done is it's added a new data file called plotter to the project, and it's, if you were to look in the directory, it'd be in the directory you're working. And every command that is used, and every setting that was used to make that plot, which I just interactively drew, I added the history, I added the zones, I picked what I wanted to plot on the zones. Those are all there. And you can adjust them because they're all variables. So you could rotate the view. Oh, well, in 3D, in 2D is probably not that interesting, but you could imagine in 3D, you could take that and say, okay, run it with this angle, and I rotate it 12 degrees, run it. And then you can actually use commands to export plots. You can do it manually, right click, plot, export a bitmap. But if you've got some of our consultants, they'll have literally thousands of plots that they have to work with, which is one of the reasons we kind of went to this whole splitting the screen, because there's only, there's a limit to how many plots you can have at one time. So they can't have 1,000 plots up at one time, which would kill performance. But you can easily bounce between those 1,000 plots. But anyhow, with between commands, and you can use fish functions. So I used to write fish functions that would step 1,000 steps and then spit out a bitmap, and then loop, step another 1,000 steps until some end condition. So once I get to 50,000 steps, I'm done. That's what I need. There's built-in tools now to sort of automate all of that, but that's the kind of thing that you can do with fish. If there's something you want to do that we haven't thought of, you can do it for the most part. Okay, so if I look back at that plot, plot 3, just really quick, and turn off the commands. So what I'm looking here are zone displacements by magnitudes. That's this guy. So you can turn those off, on. I've got some axes. You can turn off and on. You can turn the legend on and off. There's some settings under legend where if you prefer these to be decimals rather than scientific notation, you can change that. Obviously, font sizes and things like that. Model time, we have that turned off by default now, but sometimes it's nice to know in that particular plot how many steps you've had, or even what time it was generated, or the date. Maybe you need that for quality control or something. That's all. There's an actual time button, so that adds it here under the legend. Then we've got the history location, which is for that zone that we specified. And then we have an actual history. So this is a chart. I turn that off. That chart turns off. And so any history that I have, I've got 2 histories in this model. I can simply add them. I can plot one against the other. I could plot it against step by default. So if you wanted to see the load versus step, which is kind of the default, we can do that. And so you can see here, we're kind of doing a really primitive kind of stress strain type of curve. And you can imagine with a little bit more work, you could do your own kind of UCS test or even a triaxial test where you could use that for calibration.